Okay, let's look at some examples from the 4.5 homework. And we're going to start with number 8. Number 8 is just an indefinite integral, so I don't have to worry about bounds in this case. And if I look at this function, what kind of tells me that, hey, I should try integration by substitution? Well, the fact that I have a function inside of another function, right? I have a composite function that I'm working with here. So it makes for a really easy choice of what u is. Let's set u to equal 2 minus x to the 5th. Well, I can go ahead and make that substitution, and that leaves me with x to the 4th over u to the 4th dx. But remember, for me to actually be able to integrate this, I need to switch dx as well, right? I need to switch dx in terms of du. How do I do that? By taking the derivative of my inside function, of my substitution. And so I get negative 5x to the 4th dx as my derivative. Solve for dx, and I get du is equal to negative 5x to the 4th. Now I can substitute that in for dx, and I'm left with this integral of x to the 4th over u to the 4th times du over negative 5x to the 4th. What do I notice? These x to the 4th terms cancel out because I have one in the numerator and one in the denominator. The negative 5 doesn't cancel, but that's okay. It's just a constant. I can actually pull that outside of my integral by just making it into a 1/5, a negative 1/5. And so now I'm left with 1 over u to the 4th times du. Much simpler function. I have an antiderivative rule for this, as long as I recognize that I can switch this in terms of a power function. This is the same thing as u to the negative 4th. And now I can use my antiderivative rule to find the antiderivative. I get negative 1/5. I'm going to add 1 to the exponent, so negative 4 plus 1, and then I'll divide by that same number, negative 4 plus 1. Since this is an indefinite integral, I need a plus c at the end. And so I get negative 1/5 times u to the negative 3 over negative 3. And I'm left with 1 over 15u to the 3rd power plus c. So I had a function inside of a function, so I made a substitution. And because I had this x to the 4th here, it's close enough to the derivative of my inside function that I was able to cancel out the x to the 4th when I switched dx in terms of du, and therefore I was able to solve it. Okay, let's look at the next homework problem, and this is number 11 from the homework. And you'll notice, hopefully the first thing you notice is the fact that this one has bounds. So now we get to look at how integration by substitution works when I actually have a definite integral, when I have bounds. And the other reason why I chose this one is if I look at this, I don't necessarily see a function inside of a function right away. I don't see parentheses, I don't see a square root, I don't see an exponent, or I don't see an exponential function. So where's my inside function? Well, take a look at the denominator. I have a pretty complex denominator, and because I have addition and subtraction in the denominator, I can't split this up into separate fractions. So what that does is that gives me my inside function. Can I just set my inside function to be the entire denominator? That'll simplify my function if I have a much simpler denominator. So let's let u equal x squared plus 5x minus 5. So by doing that, of course, I'm now going to have this integral of 2x plus 5 over u. Now my entire denominator is now just u. But what else do I have to do? Well, first off, like we know, like we've talked about already, I need to switch dx in terms of du. How do I do that? I can do that by coming over here and taking the derivative. So the derivative of my inside function, I get 2x plus 5. X squared, the derivative of x squared is 2x, the derivative of 5x is 5, and then the derivative of negative 5 is just 0. Now, what do we notice? Look, notice how that perfectly matches this function that's in the numerator. And that's a great sign that, yep, we did this correctly. This integration by substitution is going to work. Okay, so from here I can do it one of two ways. Since I can already see that 2x plus 5 dx matches this 2x plus 5 dx, then I can go ahead and just take both of those out and replace it with du. Or I can solve for dx, and I get dx is equal to du over 2x plus 5 plug that in, and I get u 2x plus 5 over u times du over 2x plus 5. The 2x plus 5's cancel, and I'm just left with this integral 1 over u du. Now, I have purposely not done anything with the bounds yet because of the conversation we had in the concept video, where these values and the bounds start as x values because this initial integral is in terms of x. So those are x values. If I were to put these, I mean, technically I'm okay putting these as x values because my integral is still in terms of x, but if I were to put these as x values here, that would be incorrect because my integral now is in terms of u. So how do I switch these x values in terms of u? I can come back up here to my substitution and say, okay, well, what is u when x is equal to, I can plug in both of my bounds. So there's my lower bound, there's my new lower bound, and then if I plug in my upper bound, I get 19. So there's my new upper bound. So by plugging my x bounds into my substitution function, I can get my corresponding values for u, which were a lower bound of 1 and an upper bound of 19. So now this integral is correct because now it's an integral in terms of u where my bounds are actually u values. Now I'm ready to find the antiderivative. Ooh, we haven't seen this one in a while. What's my antiderivative of 1 over u? That's where I get the natural log of u. And then that's evaluated from 1 to 19. Now this is what I was talking about in the concept video, where now that I have it in terms of u and I'm done taking the antiderivative, I might think, oh, well, now I need to plug my function of x back in for u. But remember, we've already switched these bounds in terms of u. And therefore, I don't need to replug my function back in. I can just finish this right now. I can say, okay, well, this is equal to the natural log of 19 minus the natural log of 1, right? That's just me plugging in my upper bound, plugging in my lower bound, and subtracting them. Natural log of 19, that's something you just use a calculator for, but since it's positive, I don't need to worry about the absolute value. Minus natural log of 1 is just 0. And so there's my answer. So normally I only do 2 problems in these examples videos, but I did want to talk about one more problem. This is number 7. And the reason why I wanted to talk about this one is this one can be a little tricky. Looking at this problem, I can see a function inside of a function. And so I might think, let's use this function x to the 4th as my substitution. Let's substitute u for x to the 4th. But my problem is if I tried to do that, what's my derivative of this? My derivative would be 4x to the 3rd power dx, but I don't see an x to the 3rd power anywhere in my function. Meaning I will probably not be able to cancel out an x cubed if I try doing this for my substitution. So is this a problem where substitution just doesn't work? Well, no. Instead, I'm going to approach this a different way. Notice the hint. Use properties of logarithms. Remember, there's a log property that says if you have the natural log of some value raised to an exponent, you can move that exponent in front as just multiplication. And that's exactly what I'm going to do here. I'm just going to move this 4 in front as a constant. So 4 times natural log of x over 9x dx. And that makes my integral way simpler. In fact, I have some constants that I can push outside of the integral so that I don't have to worry about them. Both the 4 and the 9 I can bring out in front. And now I'm just left with the natural log of x over x dx. Now the problem is I still don't know how to integrate this. But I can still use integration by substitution to help. How? Well, just like I did in the last problem, I chose to take my whole denominator and substitute u for that whole denominator. Why? Because the denominator was what was making it complicated. If I look at this problem, what's really making it complicated? If it were just the x on the bottom, I would know how to take the antiderivative of that. But I don't know how to take the antiderivative of the natural log of x. So therefore, that's what's complicated here. So let's try choosing my u to be the natural log of x. Let's substitute u for natural log of x. That would make things a lot more simple because we don't have to worry about logarithms anymore. So if I do that, then of course I have to take the derivative in order to switch d of x. I get du is equal to derivative natural log of x is 1 over x, so 1 over x dx. I'll solve for dx by multiplying by x on both sides, and you're left with x times du is equal to dx. Let me rewrite it. I get 4 over 9. The integral of natural log is just, the natural log of x is what I set u to equal, so that becomes u. I've got an x in the denominator, and dx is now equal to x times du. What do we notice? This x over here cancels out with that x that's in the denominator, leaving me with a nice, simple, indefinite integral, u du. So now at this point, you can probably finish. So I'll leave you there because that's a nice, simple antiderivative. I'll give you a hint. This is just u to the first power. So use your power rule. But the tricky part about this one is, first of all, you have to use that property first. Don't be fooled. I don't want my inside function to be x to the fourth because then I won't be able to solve it. Instead, use your log property and then choose that natural log as your inside function, as your u, then do your substitution. Okay, good luck with the rest of the problems on the homework. Please reach out if you have any questions, and I'll see you in the next video.